outside that range in our labs. Okay, so let's take a look at the ideal gas law. How can we use these measurements? So the law itself is this equation, PV equals nRT, and it relates all three of our properties. And it also relates the number of moles, how many particles of gas we have. R is what we call a constant. In particular, it is the gas constant. It can have different units, but when it has different units, it changes. So when we use the gas constant with these units, liters, atmospheres, moles, and Kelvin, our other variables have to also have those units. So our pressure has to be in atmospheres, our volume has to be in liters, and as we said before, temperature always has to be in Kelvin. We will eventually see R with different units, not in this chapter, but you could theoretically substitute bar for atmospheres, but you'd have to change that 0.08 to a slightly different number. We could use milliliters instead of liters, but then we would have to change it by a factor of 1,000. All right, so when we're doing a calculation, doing the ideal gas law, we have to use these units. In particular, you need to know you have to use Kelvin because it doesn't matter whether we're using this equation or the ones we'll go over on Friday, you have to use Kelvin all the time. All right, so let's do an example. In this case, I've given you everything in the units that we need. So we're just working with how to rearrange the equation. So what is the pressure of 0.321 moles of an ideal gas at 298 Kelvin, sealed in a 5.20 liter flask? And then I've given you R. I will always give you R. You do not need to memorize it. So the first thing I would do is I would say, okay, I'm looking for pressure, so I need to rearrange this equation, PV equals nRT, so that I'm solving for the pressure. That means I need to get P by itself. How do I get P by itself?
Divide by V.
Divide by V, divide by the volume. Okay, so that's what that's going to look like. The volume will cancel on the left-hand side, and then what's on the right-hand side is what we'll be plugging into. The next thing I would do, because I have a lot of different numbers in my equation, I want to match up the numbers with each of those variables. So I'm going to identify my numbers. P, of course, I don't know because that is what I'm looking for. Which of those three numbers is the volume? Yeah, 5.20 liters. It's going to be the volume. Which of those is going to be the moles? 0.321. And then that leaves our last one, the 298, to be our temperature. Okay, so anytime we've got several different numbers, it's a good idea to identify which number means what. Then we have to plug those numbers into the bottom equation on the left-hand side there, making sure they're going into the right spot. And then where R is, we're going to use that 0.08206. It's going to look something like this. Once you've got that written down, plug it into your calculator and see what you get.
So we always divide by the velocity.
Remember, V is volume.
Volume.
It depends on what you're looking for. So the next problem we are going to be looking for, I think it's moles, in which case we won't. It depends on what you're looking for.
1.5.
Right, so we've got somebody up front here with 1.51.
What I forgot, whatever you remember.
Yeah, so we've got three sig figs here, so 1.51 looks good. So anybody agree with Mason? Yeah, I see some nods there. Nobody would dare disagree. He's right. 1.51. All right, put the units in your equation so that you can see I've got moles here, and then I have a whole bunch of units here, but moles is on the bottom of those units, so those cancel. Kelvin's on the bottom, and that cancels here. Liters on the top, and that cancels with liters on the bottom of the whole fraction, leaving us with atmospheres, so my units are atmospheres. All right, the next example problem, we're going to have to do some conversions. Anybody need this slide still? Okay. So the temperature of a gas is 21.3 degrees Celsius. The volume is 875 milliliters. And the pressure is in millimeters of mercury. And this is what you'll do in lab because you'll be looking at the actual barometer. So you'll see how many millimeters of mercury it is. So the pressure is in millimeters of mercury, and we want to know how many moles of particles are in this gas or present in the gas. So we want to rearrange PV equal nRT to solve for moles, which is N. We've got too many M's in chemistry. So that means we're going to have to divide by the stuff that is next. So our rearrangement is going to start out like this. We divide both sides by the RT. That will get N by itself. All right, then we want to make sure that we have our units correct. So for the pressure, we're going to have to change that to atmospheres. So we're going to divide by 760. Right? So figure out what it is for the volume and the temperature. What are the correct units there? Now we've been converting milliliters and liters for a while, so we should be able to do that one. And for the temperature, it's 273 degrees that we add. 273.1, I guess. Our rearranged equation. Oh, don't forget R. That there for you.
R is always that.
Yes, and I will always provide it for you. This is our equation solved for N. So now plug in those numbers. See what you'll get. Right, when I advance the slide, it's going to have the appropriate numbers. It's not going to show the calculation. So that's just to save us some space. When we plug it in, it should look something like this. Nothing new on the left-hand side. You don't need to rewrite that. It was still the same as what it said before. This is just the new stuff here. All right, I get 0.0343 moles. Anybody else get that? See a couple of nods. So on your quiz, I will try to remember to put that for you, but by the time we get to the test, you should have done that enough that you'll have that memorized. So I won't give you that conversion on the test. That's not for several weeks. We just took a test, so. All right, so questions on this? Anybody still need some time to catch up? Okay, I see a few nods, so I'll wait. Now, as I said, the ambient conditions are constantly changing, even indoors. You know, this classroom a month ago was super hot, and now I'm wearing a sweater and I'm still a little bit chilly. So we have changes in temperature, we get changes in pressure day to day. So if we're trying to compare gases or chemical reactions involving gases, we kind of want to have a set thing to compare them to. So we use what is called STP, or standard temperature and pressure. We use this because the ambient conditions are constantly changing, and that helps us to compare gases and reactions. So the standard pressure is 1 atmosphere, and the standard temperature is 273.15. So that's a well-established number for the freezing point of water. and it's more realistic than using something like 1 Kelvin. But if we tried to use room temperature, well, rooms are different temperatures, so that's why they kind of picked that one. Unfortunately, in our next chapter, the standard for temperature is going to be different. I didn't do it. I'm sorry. Chemists are just like that. So for gases, standard temperature is 273.15 Kelvin. And so sometimes you will see what's called a molar volume. When they talk about the molar volume, they're usually talking about it at STP, or standard temperature and pressure. And so we might ask ourselves, what is that molar volume? So we can use the ideal gas law to determine what it is. So we've got a pressure and our temperature from STP. R is always the same, and if it's a molar volume, then it is per 1 mole. So we're just going to have to plug all of those numbers into the ideal gas law and solve for volume. Okay, so this time volume is going to remain by itself, and we'll divide both sides by pressure. Plug things in, it should look like that. Calculation wise, it's nice that you have 2 1s in there, so really you're just multiplying 2 things. 22.4. So we usually say 22.4. I think because we have 4 sig figs here and here, we could say 22.41 if I remember correct. So this beach ball, you might have seen it around the department. In theory, this is 22.4. I happen to know that when it's not inflated fully, like right now it's not inflated fully, it comes in a little under that. And it does look a little bit small. So this would be 1 mole of a gas, but remember, this is 1 mole of a gas at 0 degrees Celsius. Is the air in here 0 degrees Celsius? No, so this is probably less than 1 mole. At room temperature, it would be more like 24.4. So it'd be a little bit bigger than this by about a gallon. Maybe if we extended it out just a slight amount, we would have that extra gallon. Okay, so you should be able to do the first part of active 15, which is on pressure. You should be able to do active 16, which is using the ideal gas law. The second part of 15 uses the combined gas law, which we will talk about on Friday. Don't forget about the extra credit opportunities. I hope to see some of you this evening for our website.